homework that she wants us to do for tests coming up in 2 days. But then the last two, after these two are due, then there's 2 more. And those are the ones that are for the test tomorrow.
Okay. So you want to go through this problem?
Yep.
Okay. Let me read it. All right, let's see. The acceleration of the particle is going to be the derivative of the velocity. So the velocity is going from -4 to 7 between 32 and 40.
Mm-hmm.
So if we're estimating the acceleration at 36, let's see. What would happen if, I'm not quite sure what they're looking for here in terms of technique, but I think I can probably figure.
Yeah, I can send you the answers.
Well,
how she did it.
All right, before you do that, let's have a look at what the curve might look like here. The time axis goes from 0 to 40, and v of t, which is your y-axis, goes 3, 5, -10, -8, -4, +7. So if we were to make it a continuous curve, it looks something like that. And they want us to estimate, let's see, this point right here was at 32. So what are they asking? They're asking for the slope of the curve, right? That's what acceleration is that if I take the first derivative of this velocity function, I'm going to get the acceleration function. So what I really want to do is measure the change from 32 to 40, and it's equidistant between both. So from 32 to 40, I'm gaining 11. I'm going from -4 to 7. So the average rate of change is 11/8, which is, the bottom is 40 minus 32, the top is 7 minus a -4. And so if the average rate of change of that between 32 and 40 is 11/8, then I can assume that at 36 it's halfway there. So it's going to pick up 5.5 or get to 1.5. But in terms of estimating the acceleration of the particle, I would say 11/8. Indicate units of measure. You know, it might be useful if you send me the answer so I can look at the way she's doing it and make sure that I'm not terribly off in my technique and stuff.
I think I just looked at it and you did that one right. That one's good.
Okay. Indicate units of measure. Well, what would the units of measure be?
It'd be meters per second.
Per second. Meters per second per second. That's what that's what acceleration's always going to be in. In other words, position, if you think about the three functions we're talking about, which is the position function, the velocity function, and the acceleration function. The position function is usually represented by s of t, and that's measured in meters. The velocity function, which is the first derivative of position, is measured in meters per second. And the acceleration function is the first derivative of velocity, so it's meters per second per second. Well, actually, meters per second squared. All right. Let's see. Let's look at B while I'm waiting to see what she said with that. Using correct units, explain the meaning of the integral of the velocity function from 20 to 40 in the context of this problem. What happens when you integrate a derivative function?
You get the original function?
Well, you get the total distance traveled by the original function. In other words, this is the velocity of a particle moving along the x-axis. So it's going back and forth on the x-axis. If I want to know the net distance traveled, which is, what's the word I'm trying to think of? Can't think of it. There's two things. There's the net distance traveled and there's the total distance traveled. In other words, if I'm going back and forth on the x-axis, here's the x-axis, well, my particle starts there and it goes there and then it goes back and then it goes back and then it goes back and then it goes back. Well, I can figure out where it ended if I know where it started by integrating the velocity function, and that's going to tell me how far it traveled. So the meaning of this is, displacement, the word I was trying to think of. This would be the displacement from 20 to 40. And yeah, if I want to calculate that, since I don't have the function, I merely have points on the function, well, I can quite easily use the trapezoidal method. 3 intervals. So I'm going to break the x-axis. Why would they do 3 intervals? There's 20. Only reason I don't understand 3 intervals is because 3 doesn't divide evenly into 20. So we have to break up. If we're going to do the trapezoidal method, we would have to break this thing up into 3 trapezoids, like that. There's 1, there's 2, and there's 3. You want to go through the trapezoidal method? It actually can be quite helpful. And
yeah, I haven't been there in a while.
You haven't been there in a while? Okay, let's talk about it. First of all, you need the area of a trapezoid. What's the area of a trapezoid?
It's base times height divided by 2, I think.
Well, it's good to remember it as base times height, but it's average base, because a trapezoid doesn't have a consistent base. It has 2 different bases.
It's like B1 plus B2 times height divided by 2.
Exactly.
Yeah.
Okay. Well, the trapezoids we're looking at here aren't the kind that I just drew, where the bases are parallel and horizontal. In these trapezoids, the bases are vertical. Okay? So if I'm going to use the trapezoidal method here, I need the height of that base, I need the height of that base, and I need the distance between the two of them. Well, I'm going from 20 to 40. Did she really say break it up into 3 intervals? With 3 subintervals. Yep. Okay. So if I look at my first trapezoid here, I'll put a big 1 there. What's base 1 equal to?
Base 1 would be just the function? How would be? It
would be minus 10.
Oh.
In other words, that value, that value that I put at 20 was minus 10. So base 1 would be minus 10. Base 2 would be approximately at 27. I'm going to estimate the value of v of t at 27 to be minus 7.
She said 8 for that one.
Minus 8? All right, I'll go with that.
Plus a negative 8.
That's why it's strange to divide that into 3 intervals. If you divided it into 4 intervals, it'd be perfect.
Yeah.
Well, not quite perfect, because we don't have a value for 30. But 3 intervals doesn't make a whole lot of sense. 4 intervals, at least we could go from 20 to 25, 25 to 30, and so forth and so on. But we can still get the same principle here. So, and what's the height?
5.
Well, not if we're dividing it into 3 intervals. That first interval, it's got to go from 20 to 27. Second interval's got to go from 27 to about 33, and the third interval's got to go from 33 to 40. In other words, actually 26 and 2/3, and if we want to get into fractions, if we want to use approximations, I can do that, but the key is to figure out the area of each trapezoid. Well, the area of trapezoid number 1, if I estimate this height as minus 8, the average base is minus 9, the distance from 20 to 27 is 7, so that has an approximate area of minus 63 for 1.
I don't know, she didn't, I just looked at her head and she has different things. It's weird looking.
Let me look at what she sent here.
Can't really follow her work.
Hold on. Gotta make room. Let's see what she's done here. So the acceleration is to the derivative of the velocity. That's what I did. That's exactly what I did. So she got 11/8. And then the displacement in meters of the particle from time 20 to time 40. That's also what I did. Notice what she didn't do here. She didn't divide it into 3 intervals. How many intervals did she divide it into?
She did 4.
4. Exactly, the logical number you would use to go between 20 and 40, not 3. Only thing is, you know what? She did divide this one. What did she do here? She had 10. She used minus 8 because she used 25 as the end of the first interval. That's how she got the minus 8. And 5 was the width between them. Oh, I see what she did. I thought the instructions said use 3 equal intervals. No, it just says use 3 subintervals. Well, it's true. They don't have to be of equal width. And she's made the first one 5 because she has points at 20 and 25. She made the second interval going to 32 because she knows those two values. And she made the third interval this crazy looking thing here, which is an average of a minus base and a plus base. So even though that's not really a trapezoid, you can still use the same formula, and the distance between it is 8. All right. It's an interesting way to do it. I see what she's done. Yeah, it's fine. And then C says, for t between 0 and 40, must the particle change direction in any of the subintervals indicated by the data in the table. So she's saying that in these 3 intervals that she drew, does the particle change direction ever?
From that entire thing. So the graph is of velocity that we're looking at, right?
Yes. And here's the first interval, here's the second interval, and this whole thing is the third interval, even though that's not a trapezoid. She's treating that as one interval as opposed to 2 trapezoids or 2 triangles. So what does the velocity have to do to change direction? Has to either
And then the velocity will change from positive to negative or negative to positive.
Exactly. And it does that right there at 36. In other words, just going to 0 just means it stops. So the particle is stopped right there because the velocity is 0. But down here, the velocity is negative, meaning it's moving to the left. Up here, the velocity is positive, meaning it's moving to the right. So you can't go from the left to the right without stopping. The rest of that question say, let's see. Okay, so we answered C. What does she say for C? Particle must change direction. Oh, between 8 and 20, did I miss? Oh yeah, I'm sorry. Between 8 and 20, it went from positive to negative also. But that wasn't one of her 3 intervals. I thought her question meant in the 3 intervals you used to do the trapezoids, does it change direction? Oh no, she says from 0 to 40. Okay. So yes, in this interval from 8 to 20 it changes direction. It does not change direction from 0 to 8, at least not that we can tell. In other words, we only have discrete points there. Could be that it went negative at 4 seconds. We don't know. Doesn't change direction in that interval or that interval, but those 2 it does. So, okay. Suppose that the acceleration of the particle is positive for 0 to 8. Explain why the position of the particle at 8 seconds must be greater than 30 meters. And it started at 6 meters. Now let's look at her screenshot here. It's actually a little bit easier to see, I think. Okay, what the question said what?
I have to get that one.
Explain what? I'm sorry, what?
I don't have a set D and E yet. Okay,
so we need to figure out why it has to be greater than 30 meters, right? From 0 to 8. Well, according to the table, she's accelerated from 3 meters per second to 5 meters per second. And she started at 7 meters. So even if she went 3 meters per second all the way up to 8 seconds and was still going 3 meters per second, how far would she travel? If this was a 3, in other words, if she had constant velocity between 0 and 8 seconds, she would go 8 times 3, 24 meters.
3, yeah. 24.
Starting at 7, she's past 31.
Mm-hmm.
And notice that I had to assume, which she states, she says, suppose the acceleration of the particle is positive. Well, if the acceleration of the particle is positive, at no point in between these times can she go less than 3. In other words, if we had a measurement at 4 seconds, it has to be above 3 if she is accelerating positively during the whole time.
Mm-hmm.
So there's no way there can be a number between 0 and 8 less than 3, and we just showed that even if she went from 3 to 3, she would still be past 30 meters. And she goes from 3 to 5, so she's definitely past the 30-meter spot. Let's see what her explanation is. Oh, this must be what you're... Okay, let me pull it up. That's what you were probably trying to say, and I couldn't understand. I think I know this teacher. I've worked with students of hers. I recognize her handwriting. She's been doing this for years on all these tests. Okay, so the position, she described it a little bit better than me. The position is equal to the starting position plus the displacement in the 0 to 8 seconds. And I say displacement because distance and displacement are different. Displacement is the change in the position. Distance is the total distance traveled. But because we know acceleration is positive this whole way, then velocity is increasing. The smallest value that velocity could be is 3. So we do the integral of 3, evaluated at 8, gets the same answer I got, 7 plus 24. All right. Let's look at the last part of this. Find the average value of the acceleration of the particle from t equals 0 to t equals 25. Well, what's the formula for average value?
Is that the, we're going to take the integral
all divided by 1 over b minus a, which in this case is 25 minus 0. It was from 0 to 25, right? Yeah. So,
could you hold on one second? My little bag just opened on my door and I need to go close it so it's quiet.
okay.
Why don't you close it, damn it?
All right, I'm back.
Okay. So here's the general formula for average value. I like this teacher. I like the way she always starts the answer with the general formula. Okay? And the question was the integral of the acceleration. Well, we don't have an acceleration function, but notice that the integral of the acceleration is the velocity function, right? The antiderivative of acceleration is velocity. So it turns out to be 1 over 25 minus 0, or 1/25th, times the velocity function evaluated at 25 minus 0. And we do have points for each of those. At 25, it was minus 8. At 0, it was 3. So the average acceleration from 0 to 25 is a minus 11/25. Minus, that means she must have slowed down. So that means that, yeah, she was going 3 meters per second at 0, and she slowed down to -8 at the 25-second mark. So we would expect the negative acceleration there.
Okay.
All right. What else we got? You sending me more stuff?
Yep, I sent you the next one.
Okay.
It should be like a tank-looking thing.
Those problems about particles moving along the x-axis, they can really make questions hard. I didn't see any on this, you're lucky, but the hardest questions to answer are, when is the particle slowing down and when is the particle speeding up?
Yeah, we used to get there a lot.
And the reason that's hard is because if the particle is accelerating to the left, it's speeding up, but its acceleration is getting more negative. So its acceleration is actually decreasing, and yet the particle is still speeding up. And that just kind of confuses things. Okay. I wonder why this first email, or this one said sent via Sam. You have a Galaxy 4?
Yeah.
Yeah, that's a good phone, my
I
son.
normally have to delete that, but yeah, that's a good one. I normally have to delete that, but I just got tired of deleting it.
Oh, okay. I was just curious. I was curious as to why it didn't come through on the first two and it came through on the third. But I'm not getting that email.
Yeah, I got I think it's under the first one. There's two things. Can you see my mouse?
No, I can't. I can toggle it.
I feel like I can control your computer.
Well, you could. I could turn over control of my mouse to you.
But if you look under the, I sent 3 emails, but under the first one I sent, there's 2 parts to it.
Ah, okay.
That one.
Where's the second part? I only see
Right
it
there.
over here on the right. No, those are recent photos.
Yeah, it's that one that your mouse is on right there.
Oh, okay, and that's a file I hadn't seen yet. Oh yeah, okay.
And then the answer should be coming shortly because I sent it.
Okay, well let's look at it. We won't need the answers for a moment here. Erase this. Go down one. Okay, so we have a situation where we have water going in at a certain rate and water coming out at a certain rate. Both of those, whenever you see the rate, or whenever you see that something is a rate, like cubic feet per hour, you know it's a derivative. When you see the word rate, you know it's a derivative. Okay? I'm finishing reading it here. Use the midpoint Riemann sum with 3 subintervals of equal length to approximate the total amount of water that was pumped into the pool during the time interval 0 to 12. P of t is the formula. The time interval water is pumped into the pool at those varying rates. So P of t changes. leaks out at a constant rate, or a rate defined completely by this function. Okay. So, if we look at just P of x, or P of t, at a rate of 0 there, we're going to divide this into 3 equal segments of 4 units each. And we have values of 0. We'll call that 46. We'll call this 53. We'll call this 57. Call that 60. Call that 62. And call that 63. So, if we want to use Riemann trapezoids, no, use the midpoint Riemann sum. So we're going to use rectangles. And we're going to use rectangles that go through the midpoint. So the amount of water that was pumped into the pool is the area under the curve.
Mm-hmm.
Integral or net change, integral as net change. When we have a derivative function and we want to know the total amount of water pumped in at a certain rate that changes over time, we take the integral of it, or approximate the area under the curve using this method. Well, this point right here is 46. This point right here is 57. And this point right there is 62. So what's the area?
Just 4 times 46, 4 times 57, and 4 times 62. Just add them up.
Okay, that's pretty straightforward. Show the computations. Okay, calculate the total amount of water leaked out of the pool during the time interval.
I got 660.
Did you just take the integral of that function?
Oh, no, that was what I got for that. All that.
Oh, for the other? Yeah. What does that say? Does that say minus 0.05t?
What was that saying?
The leak function, R of t.
Oh, yeah, 25 e to the negative 0.05t.
Okay. So to find out how much total water leaked out, we're going to integrate that function from 0 to 12, right?
Mm-hmm.
Well, that's pretty easy integral to do. You want to put that into your calculator, or you want to do it by hand? You know how to integrate that by hand? What's the integral?
I don't like that e or negative.
We can take the 25 out. So all we have to do is find the antiderivative of that. That's actually pretty easy. It's e to the minus 0.05t divided by minus 0.05.
Mm-hmm.
In other words, it's always the same thing divided by the coefficient of the variable, assuming it's to the first degree. If that's squared, it's a whole different problem. In fact, if that's squared, there's no integral. There is no antiderivative for this right here.
All right.
Uh-huh. The only way to integrate that function is to use an approximation using infinite series. That's the C part of Calc BC, is where you use infinite series to integrate functions that don't have antiderivatives. Who knew? Who knew that you could have a function that didn't have an antiderivative? But there certainly are some. So this is fairly easy.
I got an answer for that.
All right. You can check and see whether it is correct as easily as I can.
Yep, I got them both right.
Okay. And finally, find the rate at which the volume of water in the pool is increasing at time t equal 8. In the second part of that question, how fast is the water level in the pool rising at r equal 8? Which is a related rate problem. So first of all, let's figure out the rate that the volume of the water in the pool is increasing at t equal 8 hours. How am I going to do that?
At 8 hours, could we do the two numbers to the left and the right of it? And then add
Well,
it?
we actually have a value at 8 hours of how fast it's increasing, or how fast water is coming in. But how fast the volume of the water is increasing is a function of how fast it's going in minus what's coming out. So we know that it's going in at a rate of 60, but it's coming out at a rate of 25 times e to the minus 0.05 times 8. In other words, at 8 seconds, just plug in 8 for t and you'll find the leak rate. Subtract that number from 60 and you have the effective change in volume that's taking place at 8 seconds.
Okay. Did we do number C? I don't think we did.
Oh, no, we didn't, did we? Yeah, okay. Well, number C is adding the total amount that goes in, subtracting the total amount that came out to approximate the volume of water in the pool at time 12 hours. Let's see, hold on a second. No, that's not what I meant to say. Part A, we calculated the total volume of the water gone into the pool. Calc B, we calculated the total amount that leaked out. So by subtracting those two numbers, we should figure out how much was added. And do we know what started? We can figure out how much there was in to start, because contains 1,000 cubic feet at time 0. So the amount that was added is the total amount added minus the total amount leaked out. And we figured that in A and B.
Alright, so just be 1,000, I got 660 plus 660, and minus the number that came out, it's 225.
Okay.
And 1,434.
Okay. And did you add that to 1,000, or let's see, C says, yeah, they want the amount of water in the pool at 12 hours, so we need to take the amount that started with at 1,000 and add whatever the net that you came up with was.
Yep, I got it.
Okay. Now, D. Find the rate at which the volume of water in the pool is increasing at t equal 8. Well, got that. We know that the rate that it's coming in is 60, and we know the rate that it's going out is that. So the difference in those two rates is the rate that it's coming in. Now, the last question is the most interesting one. Volume is equal to pi r squared times h. They want to know how fast the water level is rising at r equal 8 hours. Well, that is dv dt, evaluated at 8.
Mm-hmm.
Well, how are we going to get dv dt? We're going to have to implicitly differentiate this volume here. Now, when you implicitly differentiate, we're trying to find dv dt. That's what they've asked about, right? Find the rate at which the volume of water is increasing at t equal 8. So, dv dt is equal to pi times 2r dr dt times h, or just 1, times dh dt. So when you implicitly differentiate this thing relative to a variable that is not in the equation, every variable you run into, you differentiate it and follow it with a d of that variable over dt. Okay, so this is valid, but dr dt is not changing. The radius of this pool never changes. It's always 12 foot.
So you can just plug in this 12 for the radius. And then we take the derivative of that.
That presents us with a problem. Oh, first of all, I didn't implicitly differentiate this properly. I got to use the power rule. Okay.
So we're trying to find dh dt.
Well, no, we're trying to actually find dv dt.
Well, it says, well, because we want to figure out water pool rising. So how fast is the level of the water in the pool
You're
rising?
right. You're right. Absolutely right. There's two questions here. Find the rate at which the volume of water is increasing, which is dv dt, and how fast the water level in the pool is rising is dh dt. Now, since r is a constant, I might be able to get away without differentiating that. In other words, if I do this...
Just plug in 12 into the radius.
Yeah. The problem is I have two variables here. I have this, and I have this. But they want
value we got earlier, that was dv.
Yeah, at t equal 8 hours, and at t equal 8 hours, we know what dv dt is, don't we?
Yeah, we did. I complicated it. And
yeah, we already calculated.
33.2, yeah, that was it. Yeah.
Okay, so that was the answer to the previous question, right?
Yeah, that was 43.2, sorry.
43.2?
Yeah.
Okay, so now is all we have to do is...
Plug in 12.
Nah. Where are we going to put in the t equal 8 hours?
That's what dv/dt, we plugged that into that equation, and we got that.
Well, did you send answers on this one also?
Yeah.
Let me look and see what she said, just because it'll expedite things. The second screen? No. Oh, you sent another one that's the screenshot? Good. Answers, yeah. Let me look and see what she said here. Related rate problems are not that hard, but for some reason this one's screwing me up here. Since R is not changing, we can plug in 12 before we differentiate. Okay. So V is equal to 144 pi H. Implicitly differentiate that. Plug in what we got from the previous answer. So we get a number for dH dt. Where'd she use the 8? Oh, the 8 was used to get, in other words, she said at 8 because the previous question had said at 8. So we already figured it out at 8. And that's how we got the 43.24, yeah. Okay. All right. That's what was confusing me. All right. Let's see. More, right?
Mm-hmm.
Yeah.
No, these ones are different. These ones are better.
Okay.
This is the area under the curve. This is what the test is on the bottom. There's 2 questions.
Okay. Close this all out. When you take these pictures, if you back up just a hair, you'll get in the whole thing, I think. You look, yeah, I'm missing a few words over there, but let's see. What does this say? Let R and S be the regions in the first quadrant shown in this figure. Okay. The region S is bounded by that. Find the area of R. Okay, there's 2 ways to do
calculator stuff.
What are the 2 ways to do this?
For R, to figure out R, we can figure out where the line crosses the y equals 2 minus the x cubed, where that crosses the x-axis.
Right.
So we can integrate from 0 to that, and then we do right minus left.
In other words, we're using vertical triangles up to that point right there, finding the area under tan of x between 0 and that intersection point. And then we're going to calculate the area of the rest of the thing by finding the area under the curve of 2 minus x cubed from that point to that point. That's one way to do it. That's not the most efficient way to do it, however. Yeah, that's 2 steps. Okay? If I divide that thing up into horizontal triangles, then the whole thing is the right function minus the left function.
Minus the left.
I'm going to go from 0 up to the y coordinate of that intersection.
All right.
Okay, now since I'm going to integrate it as a function of y, I need to change both of these functions to functions of y. Well, how do I change that into a function of y?
Just take the inverse tangent.
So x is equal to the inverse tangent of y. And in this other one, x is equal to the cube root of 2 minus y to the 1/3. Okay, so now I can also set them equal to one another first to find that intersection point. In other words, where is tan x equal to 2 minus x cubed? You can use your calculator to find it.
decimal. It's quite the decimal.
Huh?
It's a decimal.
Okay, as long as you know how to get it. And so our final expression is going to be the integral from 0 to that decimal. What is it? Approximately, what is that number?
That decibel, where they intersect is
now it's going to give you the x coordinate of the intersection. So make sure you get the y coordinate of the intersection.
Oh, okay, well it's 1.265.
Okay. Or you could take that x coordinate it gave you and plug it into either equation to figure out what y is. Okay? So from the graph, it looks like that's 0. Well, of course it's 0. So we're going to take the right equation, 2 minus x cubed, and subtract, excuse me, going to take the right equation, which is 2 minus y, the cube root of, minus the left equation, inverse tangent of y, which we know how to integrate. Well, we don't really know how to integrate it, but your calculator does. So that's the expression. I'm sure that's what she has. I don't have answers on this. That's okay. I don't need it. So that's the area of R. Finding the area of S. How are we going to do it?
S, we're going to have to do the integral, we're going to do in terms of x.
Yeah. We'll integrate it with vertical rectangles. Because
top minus bottom.
Exactly. Every part in here is this function minus that function. So only we would integrate it from 0 to the x coordinate of that.
Yep.
Okay. Find the volume of the solid generated when S is revolved about the x-axis. Okay, well, what are we going to use? What kind of shapes? Discs?
Washers.
Washers, exactly. Because once we rotate that about the x-axis, there's this big hole here. In other words, the figure that's created, let me see if I can do an approximate drawing of it. There's the shape. After we rotate it about the x-axis, it now looks like this, something like that. And so when we break this up vertically, it's going to be symmetrical also. So we should let's do outside radius minus inside radius. So we got the integral of pi
times, and then it'd be big R squared, which is the 2 minus x cubed, and then minus little r, which is tangent x squared, and dx, and then go from 0 to where they intersect, which is at 0.902.
Yep. Yeah. And that's all there is to that one. Find the volume of the solid generated when R is revolved about the y-axis.
So just do the same thing, just read right minus the would be the outside, which would be the far right, and then the inside would be.
Are we dividing this up? Which axis are your washers perpendicular to?
The Y.
Right. In other words, we're going to divide this up into washers like this and integrate from here to there. Okay? Which means we have to turn both of these functions back into functions of y again. Just like we did when we calculated the area of that.
So we already have what that equals, and then we already have the y value, so that's easy. You just put that in.
Yeah. You go from 0 to y value is 1.23 or something like that.
Yep.
And it's the right function minus the left function, or rather the right function is big R, the left function is little r. So it would be the reverse, I think, of, oh no, you're right. Well, it's not quite the same because that's a function of y, but this is a function of x, but you got the idea. Yeah, without cylindrical shells, these volumes of solids are a lot easier.
Yeah.
When you only have to deal with disks and washers. Okay. Well, did we cover everything? Or does she just give you some? She just gives you more material than you can possibly cover in an hour, huh? That's good. That's better than less. Better than less. But it feels like you have a pretty good understanding of it.
Yeah.
So your test is when? Tomorrow?
Yeah. And I'm probably making more appointments with you probably all throughout every day throughout this week, I think, except for Friday.
Do you know at what point you stop? Do you know at what point you stop learning new material and start preparing for the AP test?
I'm thinking maybe after this test. After this test, it's like a 4-day test, and then we have a quiz on.
I'm guessing that you're at the end of new material. You might have you haven't done integration. You haven't done integration by parts yet, have you?
No.
You might cover that, or work applications, or applications of integrals and stuff. I don't know. But anyway, I have a couple of AP Calc tests scanned into my computer, so I can definitely help you when it comes time to preparing for it. I got a lot of review material.
All right.
Okay?
All right.
All right, Matthew. Have a good one. Good luck.
All right. Thanks. You too.